Hi everyone. So in this video we are talking about some of the derivative basics, and I forget what section of the textbook we're in, but I think we are in now section 11.5 of your textbook, and we'll start off by recapping the last video, or what we learned in previous lessons. So number one, a function, which you might name f of x, can be visually represented in the xy plane with a curve, right? And so usually let our horizontal axis be x and our vertical axis be y. What I'm saying is, if I tell you some function like f of x is equal to x squared, I would represent this function in the plane by saying, well, let's just let y equal x squared. And then for any given value of x, like the value 2, 2 squared would be 4, and so we plot points that sort of represent our functions, and you can use a curve in the xy plane to represent a function. So that's one thing we learned in previous lessons. And then second, the derivative, which we use f prime of x to represent the derivative of that function f of x. The derivative is the slope of the tangent line to the curve at any point x. Right, so if I write, for example, f prime of the number 1, what that's referring to is the slope of the tangent line to the curve at this point x equals 1. And so for this curve, right here at x equals 1, there's only one line that could be tangent to this red curve, where it intersects the curve at the point x equals 1, and you would say that tangent line maybe has the same slope as the curve is steep at that same point. So anyways, whenever I write this f prime of 1, I'm talking about the slope of this tangent line here. Okay, so now we see how those ideas are connected. We also explained very carefully why we use this formula for the derivative. So here is our formula for the derivative given in a previous lesson, and if you want to know why this would be the formula for the derivative, you can go back and you can watch up on those again. And what we did is we used this definition of the derivative to calculate slopes of tangent lines to certain curves. We did, I think 2 or 3 examples of that. And it worked, but it did take a lot of work. And so what we're going to try to do in this lesson is teach you some shortcuts, some rules, or some shortcuts is probably a better way to put it. That's going to make things a lot easier for you whenever you need to find derivatives. And in this course in calculus, we're going to be finding a lot of derivatives throughout the semester, and so it's nice to be familiar with these shortcuts. So here are your first 2 shortcuts. If you have a function which is just equal to some constant, where so this k is just any real number, then the derivative is 0. And just to reason about this geometrically, you know that if I represent a constant function in the xy plane, well, for any value of x, the function just has some constant value, right? The slope of this entire function is 0. So of course this function is a line, it's a horizontal line, so it's tangent to itself everywhere, and so the tangent line slope everywhere would be 0, so then we say the derivative is 0. So the derivative of any constant function is 0. Okay, and this next one is called the derivative power rule. And we're going to let n, the lowercase letter n, be any real number. And then if we have a function, which is just x raised to the n power, we have a formula now for the derivative. We say the derivative is going to be n times x to the power n minus 1. So in other words, whenever you see x to some power, you're going to pull down that exponent in front, so the exponent becomes a coefficient, and x is going to get a new exponent, which is just 1 less than the previous exponent. So some examples really help illustrate this. If I let g of x be x cubed, then g prime of x will be 3x squared. Maybe one more, just to really drive in the point. If I have the function h of x, and I let that be x to the 7th power, I would say that h prime of x, the derivative here, is going to be 7x to the 6th. Okay, so now that you got a feel for it, I'm going to show you some more derivatives that you can actually reason through and get the correct derivative using this derivative power rule, even when it doesn't quite look like it. So for one thing, let's recognize that whenever I say square root of x, what I'm saying is this is x to the 1/2 power. So the 2 in the denominator translates to a 2 on the square root here. And likewise, just to pull another example out here, if I have the function, let's call it a of x, and I set that equal to the cube root of x, remember that this is, oops, hold on, I didn't mean a prime. I meant that the cube root of x is then just x raised to the 1/3 power. So whenever you see rational exponents where you have 1 divided by some natural number, then you're talking about taking that root of x. And so 1/3, x to the 1/3 power is cube root of x, and x to the 1/2 power is square root of x. And again, with like the square root, we don't usually write that 2 there, but you could, and everyone would know what you're talking about still. Okay, so then going along with our example, if this function is the square root of x, or x raised to the 1/2 power, then when I take the derivative, f prime of x, I would write it 1/2 times x raised to the negative 1/2 power. But notice, the negative power just means you can move it to the denominator and make that a positive exponent. So I can move this x to the power negative 1/2 in the numerator to x to the power 1/2 in the denominator. And then if it's x to the power 1/2, remember you could also write that as square root x. And so all of these are equivalent ways of expressing the same idea. I mean, just there's 3 different representations, right? Here, here, and here. But they all mean the same thing. And likewise with our other example that I came up with over here, with our a of x example, that means a prime of x, we can use power rule and say that this would be 1/3 times x to the negative 2/3 power, because 1/3 minus 1 would be negative 2/3. And you could write it like this, and that would be a perfectly acceptable answer, or you could write 1/3 times x to the 2/3 power. And I just want to point out here, just as an extra note, a little bonus lesson, if I have x to the 2/3 power, this would be the same thing as the cube root of x squared. Or you could write exactly the same thing, x to the 2/3 power, a different way. You could write it as x squared and then take the cube root. And so this is 3 different ways of writing the same thing, and so whenever you see x to the 2/3 power there, you could actually replace those with maybe this or this one over here, and everyone would still know what you mean, and they're all a correct way to represent the same idea. All right, more power rule examples follow, so I'll work quickly through the rest of these. Whenever you see 1/x, remember that you can also write this as x to the negative 1 power. So the negative exponent just means you move it to the denominator. So this would be the same thing as 1/x to the 1 power. And of course, you know x to the 1 power is just 1/x. But this representation allows me to use my derivative power rule. So this is easy to see that this will be g prime of x, which will be negative 1 times x to the power negative 2. So the negative 1 just makes the whole thing negative. The negative 2 power just means I move x squared to the denominator. And so I can say that my derivative here, g prime of x, is negative 1 over x squared. For example 4, here, if f of x is equal to 1 over x squared, 1 over x squared is the same thing as saying x to the negative 2 power. So that means when I take the derivative, I'll let negative 2 come out in front, and I'll reduce the exponent by 1, so it'll be negative 2 times x to the negative 3 power. And again, that negative exponent means I just move it to the denominator, which means this is negative 2 over x cubed. There we go. Okay, example 5 here. G of x is 1 over square root x, and so I can write this as g of x equals 1 over x to the 1/2 power. But that x to the 1/2 power in my denominator, I could just rewrite that as x to the negative 1/2 power. Remember, the negative means you can put it in your denominator. And I like this form because this form allows me to use my derivative power rule. And so I will write negative 1/2, which is the old exponent, times x, and then I'll decrease the exponent by 1, so it'll be negative 3/2 for my derivative. And you could put that negative 3/2 exponent. You could put x to the power positive 3/2 in the denominator. And that would be an equivalent way to represent that. So again, just to show you real quick, that would be negative 1 over 2 times x to the 3/2 power. Okay. Here we go. Example 6 tells me I have my function equal to x to the power negative 2022. So this is already in a nice format to use my derivative power rule. So I'll write negative 2022 right there, times x to the power, and I'm going to decrease my exponent by 1, so this would be negative x to the power 2023. And again, if you want to represent this in a different way, you can write negative 2022 divided by x to the power 2023. Those are equivalent ways of expressing that derivative. All right, so for example 7 here, we have this all ready to go to use my derivative power rule. So I take the derivative out in front, 5/3, and then I'm going to write x to the power, I think I misspoke, I take the exponent out in front. So I write 5/3 times x to the power 2/3. Because 5/3 minus 1 is 2/3. And then lastly, for this example 8, this would let f prime of x be negative 3.14159 times x to the negative 4.14159. And again, since that exponent is negative, you could write it as negative 3.14159 divided by x to the power 4.14159. And that would be exactly the same way to represent it would be the same derivative represented in a different way. Okay. Here's another rule, another shortcut that you should have in your pocket for evaluating derivatives. And this word, you pronounce it homogeneity. So we're talking about the derivative homogeneity rule. And what this is saying is that if you multiply some function by a constant, so like k is just a real number, then you can just take that k constant and sort of leave it alone. Let me show you with an example. So you know that you can take the derivative of x to the 5th power, but what about 7 times x to the 5th power? Well, so our derivative of 7 times x to the 5th power is just going to be actually 7 times whatever I get for the derivative of x to the 5th power. And if you've been paying attention to our power rule discussion, x to the 5th power, the derivative here would be 5 times x to the 4th power. And so basically what the homogeneity rule says is just leave that 7 alone, and the derivative becomes 7 times 5 times x to the 4th power. And so 7 times 5 is 35, and so this derivative is going to be 35x to the 4th power. All right, very good. Example 2 down here says that my function is negative 42 times square root x. And again, my homogeneity rule says just leave that constant multiplier alone. So we're going to leave negative 42 alone here. And then what would be the derivative of just square root x? Well, if I take the derivative of square root x, which we've done before, it's like taking the derivative of x to the 1/2 power. So this is going to be, in either case, 1/2 x to the negative 1/2, or you might write it as 1 over 2 square root x. So, leaving the negative 42 alone, or multiply times 1/2, and then x to the negative 1/2 power. Well, negative 42 divided by 2 would be negative 21. So you could write negative 21 over square root x. And so these are, different ways to represent the same idea. Okay, another couple of rules that should hopefully make things easy, and hopefully they make sense to you, are what we call the additivity rules. And what this is saying is that if you're taking the derivative of a sum, then that's just the sum of those derivatives. And if you're taking the derivative of a difference, where you have a minus sign, that's the same thing as the difference of those derivatives. So this corresponds to that, and if you didn't figure it out, this corresponds to that other second line. Okay, so let me just show you with examples. In example 1, we have this function, f of x, and if I want to take the derivative, f prime of x, I'm going to have to rely on my power rule to take those powers of x derivatives. I'm going to have to use my homogeneity rule to say that I can ignore those coefficients, which are 3 and 2, and I'll have to use my additivity rules to realize that even though I'm taking the derivative of the whole function, I can actually take the derivative of each of those terms individually and then just combine them again like they were. So the derivative of 3x squared is going to be 3 times 2 times x to the first power, which is 6x. And then the derivative of 2 times x, well, that will just be 2 times x to the derivative of x to the first power. So derivative of x to the first power. Let's think about that for a moment. X is just equal to x to the first power, and that derivative would be 1 times x to the 0 power, using my power rule. And x to the 0 power is just 1, and so the derivative of x by itself is just 1. So this would be minus 2 for that second term. And then the derivative of just the number 10 by itself, maybe you've forgotten, but if you take the derivative of just a constant, that is 0. The derivative of a constant function is 0. So to remind you from the very first derivative rule that we learned in this section. And so where I have that plus 10 on the end of this polynomial right here, we can just ignore that completely because the derivative of that constant by itself will be 0. Okay, And that means this is our derivative. For this g of x function, I'm going to rewrite this so I have 7 times x to the 1/2 power minus 42 times x to the negative 1 power. And so now we can write our derivative, g prime of x. We can write that as 7/2 x to the negative 1/2 power minus a negative 42, so you could just write plus 42 because I'm bringing down that negative 1 in front, times x to the negative 2 power. And if you wanted to rewrite this, you could rewrite it as 7 over 2 root x plus 42 over x squared. So there's your derivative. And for example 3, I set this one up in a nice way intentionally. The derivative of x to the 5th will be 4, no, excuse me, the derivative of x to the 5th is going to be 5 times x to the 4th, just using power rule. And then the derivative of x to the 4th will be 4 x to the 3. The derivative of x cubed is going to be 3x squared. The derivative of x squared is going to be 2x to the 1 power, and then the derivative of x is like the derivative of x to the 1 power. We already spoke about that over here. That's just going to be the number 1. And the derivative of any constant, like this plus 1, is 0. So if you want to clean this up a little bit, you can write your derivative as just x to the 4th minus x to the 3rd plus x squared minus x plus 1. All right. So now that we've learned how to use some of the most basic derivative rules that we're going to learn this semester, commit those to memory because we'll be using those a lot. I just want to point out at the end here that we have a lot of different notation that we use in mathematics that we use to represent derivatives. And I want you to be familiar with seeing every different type of derivative notation. And, when I pose you a question on a quiz or an exam or something like this, I want you to be ready to answer even if you see it in any of these 5 different formats, right? So all of these mean exactly the same thing. So if we're talking about a function where y is my dependent variable and x is my independent variable, and I'm asking what is the derivative of f of x, well, that would be f prime of x, which is what we've been using all lesson. Or if we have this definition that the value of y is just going to be the function evaluated at x, then I could write this derivative as just y prime. And maybe that's a little bit sloppy, but we've definitely used that a lot. And if you take other math classes, for sure. This is also a very, very popular way of representing the derivative. So these lowercase d's represent really, really small changes. And so what this is saying, when you use this notation, is you're saying, I'm talking about the ratio between a really small change in my dependent variable to a very small change in my independent variable. And if you, squint closely and look at the video we recorded last about rates of change and the other one about tangent lines, you'll recognize how the definition of a derivative really is the ratio of a small change in your output to a small change in your input. And so this is just another way of stating the same thing. So you could say that the derivative, or f prime of x, is equal to dy dx, and that would be totally fine. Of course, this is the same thing, just on its side, so use the little slash to represent dividing again. Otherwise, the same thing as that. And then this last little bit is saying, let me have the derivative with respect to x of the function f of x. And so that's, again, a 5th way of representing the exact same thing. What I really want to emphasize here is that those 5 examples are all different ways of using notation to ask about the derivative or talk about the derivative. And so maybe just as one last exercise before I leave you guys is if we wanted to talk about the additivity rule, right, of derivatives. So if I give you a function f of x is equal to u of x plus v of x, and then I ask you, well, what's the derivative, or what is f prime of x? I could have written this rule a different way. I could have asked, what's the derivative with respect to x of f of x? And this would be written as the derivative with respect to x of u of x plus v of x. Then, if I break it up in f of x into u of x and v of x, like our definition here. And lastly, our additivity rule would tell us that this is just the derivative of u of x plus the derivative of v of x. So new ways to write the same things that we've learned already. And I want to make a last, man, I keep making more and more last notes, but the last thing I'll say in this video, I want to scroll back up to the homogeneity rule. Whenever I worded this, as I was typing my notes, constant factors can be pulled out of the derivative operator. What I was imagining in my head was this situation where you're asking about the derivative of k times g of x. And in that case, you would say that this derivative is just equal to k times the derivative of g of x. And so that's what I mean when I say that you can just pull the constant factor out of the derivative operator. It's that you can just worry about the derivative, in this case, of this function, and you can ignore the k constant multiplier. All right.